Hi, welcome to my channel. I'm your host GL, and today I'd like to talk about density. Alright, let's break it down. Density is simply the amount of stuff packed into a given space. Mathematically, we express it as mass divided by volume. Now, imagine you're packing for a vacation. Density is like how tightly you've crammed your suitcase. If you've got a small bag stuffed to the brim with heavy winter coats, that's high density. On the flip hand, if you've got a giant suitcase with just a few t-shirts rattling around, that's low density. In the science world, we measure this packing efficiency by dividing the mass, how much stuff you've got, by the volume, the size of your suitcase. So next time you're struggling to zip up that overpacked bag, just remember, you're dealing with some serious density issues. The key here is comparing densities. If an object is less dense than the fluid it's in, it'll float. If it's more dense, it'll sink. It's that simple. Think of it like a party in a pool. The pool water is like our fluid, and people are our objects. Now, imagine you've got a bunch of people wearing different types of floaties. The kid with the big inflatable unicorn? That's like an object with low density, they're gonna bob around on top like a champ. Your buddy who decided to wear a weighted vest for some reason? Yeah, he's heading straight to the bottom, that's your high density object. And then there's you, just chilling in the middle of the pool. You're about the same density as the water, so you can float or sink depending on how you position yourself. It's all about that density dance. Here's the gist: plop the object in water, measure how much water it displaces, and divide the object's mass by this volume. Voila! You've got your density. Now, let's break it down like we're cooking up some density soup in the lab. First, grab a graduated cylinder and fill it with a known amount of water. Next, place your funky-shaped object, let's say it's a small action figure of yours truly, gently into the water. Watch the water level rise, that increases the volume of your object. It's like your action figure is doing a little science dance, pushing the water up to show off its volume. Now, weigh the action figure on a scale to get its mass. Divide that mass by the volume of water displaced, and boom. You've just calculated the density of a miniature chemistry teacher. Who knew science could be so? Figuratively speaking, in general, increasing temperature decreases density, while increasing pressure increases density. This is because heat makes molecules spread out, while pressure squeezes them together. And by the way, if you are enjoying the video so far, do me a quick favor. Hit that like button. It really helps support the channel. And it only takes a second. Picture this: you've got two identical lockers at school. One belongs to the star quarterback who's crammed it full of gear, textbooks, and probably a few forgotten sandwiches. The other belongs to the minimalist art student who's got nothing but a sketch pad and a single pencil. Same size lockers, very different contents. The quarterback's locker is like our higher density object, more stuff packed into the same space. The art student's locker? That's our lower density object. Both lockers look the same from the outside, but if you tried to move them, you'd feel the difference real quick. This is why a kilogram of lead feels so much heavier than a kilogram of feathers. Even though they have the same mass, the lead is packing all that mass into a much smaller volume, making it much denser. Water has a density of 1 gram per cubic centimeter, at 4 degrees Celsius, 39.2 degrees Fahrenheit. It's used as a reference point because it's a nice, round number and water is, well, everywhere. Think of water as the Beyoncé of the density world. It's the standard that everything else gets compared to. Just like how every new pop star gets measured against Queen Bey, we measure the density of other substances relative to water. This 1 gram per cubic centimeter is like water's hit single, catchy, easy to remember, and it's been topping the density charts for ages. But here's where it gets interesting: this density is part of what makes water so special and essential for life. If ice were denser than liquid water, it would sink, and lakes and oceans would freeze from the bottom up. Instead, ice floats, insulating the water below and allowing aquatic life to survive winter. It's like water's got its own little life-saving trick, a sort of density dance that keeps things just right for life on Earth. So next time you're sipping on some H2O, remember, you're drinking the substance that sets the gold standard in the density game. Density plays a crucial role in buoyancy, which is essential for designing vessels that float or submerge. Ships need to be less dense than water to float, while submarines must be able to change their density to move up and down in the water. Imagine you're a naval architect, fancy title for someone who designs ships and submarines. You're basically playing a high-stakes game of will it float? But instead of tossing random objects into your bathtub, you're dealing with massive vessels and millions of dollars. For ships, you need to design a hull that displaces enough water to counteract the ship's weight, keeping it afloat. It's like giving the ocean a big bear hug and making sure it hugs back with just the right amount of force. Submarines, though, are the real density dynamos. They're like the chameleons of the sea, changing their density on demand. They have ballast tanks that can be filled with water or air to increase or decrease their overall density. When they want to dive, they let water in, becoming denser than the surrounding ocean. Ready to surface? They pump that water out, becoming less dense and rising like a cork. It's like they're doing a density dance, leading to that classic submarine movie scene: dive, dive, dive. But density isn't just for sea lovers. It's everywhere. It's why hot air balloons rise, less dense hot air inside the balloon, why oil floats on water in your salad dressing, and why helium balloons try to escape to the ceiling at birthday parties. If you're looking for exercises to test your knowledge, there is a link in the description for you. Thanks for sticking around till the end. If you enjoyed the video so far and want to see more content like this, make sure you hit that subscribe button. Thanks for watching.